Subscribe to the channel so you don't miss out on any of these videos. Imagine a particle so elusive, so delicate, that it's often called a ghost. A particle that might silently weave through the universe, holding the very fabric of reality together, but no one has ever seen it. Sounds like the beginning of a sci-fi movie, right? But this isn't fiction. This is the story of axions, mysterious, hypothetical particles that some believe could unlock the greatest puzzle in physics, dark matter. Here's the thing about dark matter: we know it's there. Or at least we're pretty sure it's there. It makes up about 27% of the universe, outweighing regular matter by a factor of 5. But we can't see it, touch it, or interact with it in any way we're used to. It's like the universe is playing an elaborate game of hide-and-seek with its most important clues. That's where axions come in. These ghostly particles are one of the most compelling candidates for what dark matter could actually be. And if we find them, they could completely rewrite the laws of physics as we know them. But what exactly are axions? Where do they come from? Why do scientists think they could be the key to dark matter? And what would it mean for us, and the universe, if they're real? Let's break it all down, piece by piece, and dive deep into the strange, almost magical world of axions. To understand axions, you first need to know a little about the universe at its most fundamental level. Physics has two big, overarching theories: general relativity and quantum mechanics. General relativity explains how gravity works and how big things, like stars and galaxies, move and interact. Quantum mechanics deals with the tiny stuff, atoms, particles, and the forces that act on them. But here's the kicker: these two theories don't always agree. They're like two different rulebooks for the universe, and scientists have been trying for decades to reconcile them. Axions might be part of the solution. The story of axions begins with a problem in quantum mechanics called the strong CP problem. Without diving into the math, it basically boils down to this: one of the fundamental forces of nature, called the strong nuclear force, doesn't behave the way we expect it to. Specifically, it doesn't seem to violate something called charge parity symmetry, even though theoretically it should. This has been a massive headache for physicists. Imagine trying to solve a jigsaw puzzle, only to find that one piece is upside down and doesn't fit no matter what you do. Enter the axion. In the 1970s, two physicists, Roberto Pecchiai and Helen Quinn, proposed a theoretical mechanism to solve the strong CP problem. Their idea predicted the existence of a new particle, the axion, that would naturally fix the symmetry issue. Think of it like a tiny cosmic band-aid, smoothing out the universe's imperfections. But here's where it gets really interesting. Over time, scientists realized that if axions exist, they could do a lot more than just solve the strong CP problem. They might also explain dark matter. The reason? Axions have just the right properties. They're incredibly light, electrically neutral, and they don't interact much with ordinary matter, all characteristics you'd expect from dark matter. If axions are real, they could form an invisible halo around galaxies, including our own Milky Way, helping to account for the extra gravitational pull that dark matter provides. This would explain why galaxies don't just fly apart, despite spinning way faster than they should. Axions could be the unseen scaffolding that holds everything together. But why haven't we found them yet? That's where that ghostly part comes in. Axions are ridiculously hard to detect. They don't emit light, don't absorb light, and barely interact with anything. It's like trying to catch a shadow in a dark room. Scientists have come up with some clever ways to search for axions, though. One of the most promising methods involves something called a haloscope. These devices use powerful magnets and ultra-sensitive detectors to look for tiny signals that axions might produce when they interact with electromagnetic fields. It's painstaking work, like listening for a whisper in the middle of a thunderstorm. Another approach involves astrophysics. Axions might reveal themselves in extreme cosmic environments, like the cores of stars or the collisions of neutron stars. By studying the light and energy from these events, scientists hope to spot the subtle fingerprints of axions. And then there's the possibility that axions could solve not just one mystery, but many. For example, some theories suggest that axions could also explain why the universe contains more matter than antimatter, a question that's puzzled scientists for decades. Others speculate that axions might even play a role in the early moments of the universe, shaping its structure during the Big Bang. But the implications of axions go far beyond just solving a few scientific puzzles. If they exist, they could open up entirely new fields of research. Imagine harnessing axions for technology, or using them to unlock new forms of energy. They could even change the way we think about reality itself, challenging our understanding of time, space, and the fundamental forces of nature. Yet, as exciting as all this sounds, the search for axions is far from over. Decades of experiments have yet to produce definitive proof. Some scientists argue that we're looking in the wrong places or using the wrong tools. Others think axions might not exist at all and that dark matter could be made of something else entirely, like WIMPs, weakly interacting massive particles, or primordial black holes. Still, the hunt for axions continues, fueled by the tantalizing possibility that these ghostly particles could hold the key to the universe's greatest secrets. It's a quest that combines cutting-edge technology, brilliant minds, and a touch of the unknown, a reminder that even in the 21st century, there are still mysteries waiting to be unraveled. So, will we ever find axions? And if we do, what will they tell us about the cosmos and our place in it? The answers might be closer than we think, or they might remain just out of reach, teasing us with the promise of discovery. Either way, the journey is far from over, and the story of axions is still being written. This journey to uncover the mystery of axions is a testament to humanity's relentless curiosity. Think about it, we've mapped out continents, explored the deepest oceans, and even landed on the moon, but there's still this massive gap in our understanding of what the universe is actually made of. Dark matter remains one of the biggest enigmas in science, and axions stand out as one of the most compelling leads we have. Yet the very nature of axions, their ghost-like elusiveness, makes the search for them as frustrating as it is fascinating. To fully appreciate why axions are so promising, we need to dive deeper into their unique characteristics and the theories behind them. Axions, if they exist, are expected to have an extremely small mass. We're talking about a mass so minuscule that even calling it tiny feels like an understatement. For perspective, an axion could be millions, or even billions, of times lighter than an electron, one of the lightest known particles. And yet, their sheer number could make up for their small size. Think of it this way: a single grain of sand might seem insignificant, but when you add up all the grains of sand in the desert, you start to grasp the enormity of their collective presence. Axions could work the same way, individually weak, but collectively massive enough to account for the mysterious gravitational effects we attribute to dark matter. But axions aren't just tiny, they're also incredibly shy. They don't interact with light, or with most other particles in any significant way. This makes them nearly impossible to observe directly. Instead, scientists are forced to look for indirect evidence, subtle clues that hint at their presence without revealing them outright. One of the most intriguing aspects of axions is their connection to electromagnetism. Theoretically, axions could convert into photons, particles of light, under the right conditions, such as in the presence of a strong magnetic field. This property forms the basis of many experimental searches. For example, in a haloscope, scientists create a powerful magnetic field and then listen for faint radio signals that might be produced by axions converting into photons. It's an ingenious idea, but so far, the results have been inconclusive. Another promising method involves looking at stars. Inside stars, conditions are extreme: immense heat, pressure, and magnetic fields. If axions exist, they might be produced in these fiery environments and then escape into space. This would cause stars to lose energy in a way that doesn't match our current understanding of stellar physics. By carefully observing stars, especially those nearing the ends of their lives, scientists hope to catch axions in the act. Neutron stars and black holes offer another avenue for investigation. These cosmic objects are among the densest and most extreme environments in the universe. Neutron stars, for example, have magnetic fields trillions of times stronger than Earth's, and their intense gravitational pull warps space and time. Some theories suggest that axions could form a kind of cloud around these objects, influencing their behavior in ways we might be able to detect. For instance, scientists have theorized that axion clouds around rotating black holes could produce gravitational waves, ripples in spacetime that we can now detect with instruments like LIGO and Virgo. If we were to observe such waves with unusual characteristics, it could be a smoking gun for axions. But here's where things get even more mind-bending. Some researchers believe that axions could be tied to the concept of quantum fields. In quantum mechanics, particles aren't just tiny bits of matter, they're also waves in a field that stretches across the universe. If axions exist, they might form a background field that permeates all of space. This axion field could interact with other quantum fields in subtle ways, leaving traces in experiments we haven't even thought to conduct yet. The implications of finding axions, or proving they don't exist, would be staggering. If we find them, it would confirm that the Pecky-Quinn theory is correct, resolving the strong CP problem and solidifying our understanding of quantum mechanics. It would also provide a clear answer to the question of what dark matter is, solving a mystery that has baffled scientists for decades. On the flip side, if axions don't exist, it would force us to rethink our assumptions about both dark matter and quantum physics. It would mean that the true nature of dark matter lies elsewhere, perhaps in exotic particles like sterile neutrinos, hidden dimensions, or even entirely new forms of matter we haven't conceived of yet. But for now, the search continues. Scientists around the world are building ever more sensitive detectors, designing ever more ingenious experiments, and studying the universe with ever greater precision, all in the hope of catching a glimpse of these ghostly particles. Some are even exploring the possibility that axions could have been produced in enormous quantities during the Big Bang, forming a kind of cosmic soup that has shaped the evolution of the universe ever since. The hunt for axions is more than just a scientific quest. It's a reminder of how much we still don't know about the cosmos. It's humbling to think that, despite all our technological advances and all our knowledge, we're still in the dark, literally, about what makes up most of the universe. And yet, that's also what makes this search so exciting. The possibility of discovering something as revolutionary as axions is what drives scientists to keep asking questions, to keep pushing boundaries, and to keep looking up at the stars with wonder. The allure of axions lies not just in their potential to explain dark matter but also in how they challenge us to think differently about the universe. Their very existence forces us to reconcile some of the most perplexing paradoxes in physics, bridging gaps that have long seemed insurmountable. Take, for instance, the concept of symmetry in the universe. Symmetry is a fundamental principle in physics, suggesting that certain aspects of the universe remain unchanged under specific transformations. Yet, without axions, there appears to be a glaring asymmetry in the strong nuclear force, known as the strong CP problem. The strong CP problem arises because, theoretically, the strong nuclear force should violate CP symmetry, where C stands for charge conjugation, flipping particles with their antiparticles, and P stands for parity, mirroring spatial coordinates. However, experimental evidence shows that this violation doesn't occur. It's as if the universe is somehow fine-tuned to maintain symmetry, a scenario that feels unnaturally coincidental to many physicists. Enter the Pecky-Quinn theory, which proposes axions as a way to elegantly restore this symmetry. This isn't just a mathematical fix, it's a profound insight into the fabric of reality. Axions, if real, would serve as a kind of cosmic equalizer, balancing the equations that govern the universe. But their potential doesn't stop there. Because axions could interact with electromagnetic fields, they might leave subtle imprints on the cosmic microwave background, the faint afterglow of the Big Bang. By studying these imprints, scientists hope to uncover clues about the conditions of the early universe and the role axions might have played in its evolution. One particularly fascinating avenue of research involves axion-like particles, or ALPs. These are theoretical cousins of axions that share some similar properties, but aren't bound by the same mass or interaction constraints. ALPs are especially interesting because they could solve multiple cosmic mysteries at once. For example, they might explain why certain distant galaxies appear to behave in ways that defy conventional physics, or why the universe's expansion seems to be accelerating. But why are axions so difficult to detect? The answer lies in their ghostly nature. Axions are predicted to interact so weakly with ordinary matter that even the most sensitive instruments struggle to pick up their presence. It's like trying to hear a whisper in the middle of a roaring storm. Despite this, scientists are undeterred. They're developing innovative techniques to amplify the faint signals that axions might produce, using everything from powerful magnets to ultra-cold detectors cooled to temperatures just above absolute zero. One of the most ambitious efforts is the Axion Dark Matter Experiment, ADMX. Located at the University of Washington, ADMX uses a massive magnetic field to search for axions converting into photons. The detector is essentially a giant, highly sensitive radio tuned to the specific frequency range where axion signals are expected to appear. So far, no definitive axion signal has been detected, but each experiment helps narrow down the possibilities, bringing us closer to an answer. Other experiments, like CERN's CRIST-CERN Axion Solar Telescope, take a different approach. CRIST is designed to detect axions potentially emitted by the Sun. The idea is that axions produced in the Sun's core might convert into X-rays when they encounter the strong magnetic field of the telescope. While CRIST hasn't found direct evidence of axions yet, it has placed stringent limits on their properties, guiding future searches. Then there's the realm of astrophysical observations. Some scientists are looking at neutron stars, which are essentially giant cosmic laboratories for extreme physics. If axions exist, they might be produced in the intense magnetic fields of these stars, subtly altering their behavior in detectable ways. For instance, axions could escape from neutron stars, carrying away energy and affecting the star's cooling rate. By studying these cooling patterns, researchers might infer the presence of axions indirectly. The connection between axions and gravitational waves is another tantalizing prospect. Axions could theoretically form clouds around rotating black holes, and these clouds might produce gravitational waves as they interact with the black hole's spin. Detecting such waves with unique signatures could provide indirect evidence of axions, offering yet another piece of the puzzle. Perhaps the most exciting aspect of the axion hypothesis is its potential to unify our understanding of physics. Axions could bridge the gap between quantum mechanics and general relativity, two pillars of modern physics that remain fundamentally incompatible. By studying axions, we might uncover new principles that explain how these two frameworks fit together, bringing us closer to a grand unified theory of everything. But even if axions turn out not to exist, their story isn't one of failure. The search for axions has already driven significant advancements in technology, from the development of ultra-sensitive detectors to new ways of analyzing astronomical data. These innovations will have applications far beyond the hunt for dark matter, benefiting fields ranging from medicine to materials science. And let's not forget the philosophical implications of this quest. The search for axions is a reminder of how much we still don't know about the universe. It challenges us to confront the limits of our understanding and to embrace the mysteries that make science so compelling. Whether we find axions or not, the journey itself is a testament to human ingenuity and our unending curiosity about the cosmos. As we continue to push the boundaries of what's possible, the hunt for axions stands as a symbol of our collective determination to solve the universe's greatest mysteries. It's a story of persistence, creativity, and the enduring belief that, somewhere out there, the answers we seek are waiting to be discovered. The quest for axions encapsulates the human spirit's relentless drive to uncover the unknown. It's a search that combines the abstract beauty of theoretical physics with the hands-on ingenuity of cutting-edge experiments. To truly grasp the magnitude of this effort, it's worth considering the sheer scale of the challenges involved. Detecting axions is akin to finding a single grain of sand in a desert while blindfolded, with only a vague idea of where to start. Yet, instead of being deterred, scientists have turned this daunting task into an opportunity for innovation, crafting ingenious tools and methodologies to peer deeper into the cosmos than ever before. One intriguing aspect of the axion search lies in the synergy between theory and experiment. Unlike many scientific investigations where experiments either confirm or refute existing theories, the axion hunt is uniquely iterative. theoretical predictions about axions, such as their mass, interactions, or potential sources, guide experimental efforts. In turn, the results of these experiments refine theoretical models, creating a feedback loop that propels the field forward. This dynamic interplay exemplifies the scientific process at its finest, demonstrating how progress often emerges from the delicate balance between ideas and evidence. Take, for example, the parameter space of axions. This refers to the range of possible values for properties like mass and interaction strength that axions could theoretically possess. Early theories suggested that axions might have a relatively large mass, but as experiments ruled out these possibilities, researchers began exploring the idea of ultralight axions, with masses billions of times smaller than that of an electron. This shift in focus opened up new avenues for investigation, such as the possibility that axions might form an exotic type of matter known as a Bose-Einstein condensate. A Bose-Einstein condensate is a state of matter that occurs when particles become so cold and dense that they essentially behave as a single quantum entity. If axions can form such condensates, they might clump together in certain regions of space, creating localized concentrations of dark matter. These condensates could produce subtle gravitational effects detectable through careful observations of star clusters, galaxies, or even the cosmic microwave background. Another compelling avenue of exploration involves the potential role of axions in the early universe. If axions were abundant shortly after the Big Bang, they could have influenced the formation of large-scale structures like galaxies and galaxy clusters. By studying the distribution of these structures, researchers might infer the presence of axions indirectly. This approach relies on sophisticated simulations that model the behavior of axions under various cosmological conditions, offering a window into their potential impact on the universe's evolution. One particularly bold hypothesis suggests that axions might be linked to the phenomenon of inflation, the rapid expansion of the universe in its first moments. If axions played a role in driving inflation, they could leave behind distinctive imprints in the form of primordial gravitational waves. Detecting these waves would not only provide evidence for axions but also shed light on one of the most enigmatic epochs in cosmic history. The search for axions also intersects with other mysteries of modern physics. For instance, the discovery of dark energy, the mysterious force driving the universe's accelerated expansion, has prompted some theorists to consider whether axions might contribute to this phenomenon. While the connection between dark matter and dark energy remains speculative, it underscores the interconnected nature of these cosmic puzzles. Solving one could provide crucial insights into the others, like unraveling the threads of a tightly woven tapestry. Despite the challenges, the axion hunt continues to inspire groundbreaking experiments. One innovative approach involves using superconducting quantum devices, which are extraordinarily sensitive to tiny changes in energy. These devices could detect axions indirectly by measuring their interaction with electromagnetic fields, offering a new way to probe their elusive nature. Meanwhile, astrophysical observations remain a cornerstone of the axion search. Scientists are now looking at pulsars, rapidly rotating neutron stars that emit beams of electromagnetic radiation, as potential laboratories for axion detection. The idea is that axions produced near a pulsar might interact with its magnetic field, generating faint signals that could be detected by radio telescopes. Pulsars are especially intriguing because their emissions are incredibly regular, making any deviations relatively easy to spot. And then there's the possibility of discovering axions through gravitational lensing, a phenomenon where the gravity of massive objects bends light from distant sources. If axions exist, they could subtly alter the lensing patterns observed in certain cosmic regions, providing yet another indirect clue to their presence. Beyond the scientific implications, the search for axions has profound philosophical dimensions. It challenges us to reconsider our place in the universe, pushing the boundaries of human knowledge and reminding us of the vastness of what we have yet to understand. The idea that tiny, nearly undetectable particles could hold the key to one of the greatest mysteries in science is both humbling and awe-inspiring. It's a testament to the beauty of physics, where the smallest things can have the most profound implications. Perhaps the most striking aspect of the axion story is its open-ended nature. Unlike many scientific pursuits with clear endpoints, the search for axions is as much about the journey as the destination. Whether or not axions are ultimately found, the quest itself is a catalyst for discovery, driving advances in technology, deepening our understanding of the universe, and inspiring a new generation of scientists to push the boundaries of what's possible. As we look to the future, the possibilities seem endless. New experiments, such as those leveraging quantum computing or next-generation telescopes, promise to take the search for axions to unprecedented levels of precision. At the same time, theoretical breakthroughs could provide fresh insights, revealing connections between axions and other unsolved mysteries of physics. The story of axions is a microcosm of science itself, a relentless pursuit of truth, guided by curiosity, creativity, and an unwavering belief in the power of human ingenuity. Whether they are the key to dark matter or just another piece of the cosmic puzzle, axions remind us of the boundless potential of the human spirit to explore, discover, and understand. As we continue our exploration of axions and their potential role in explaining dark matter, it's important to delve deeper into the theoretical models that have been proposed to account for their existence, and the implications of these models for our understanding of the universe. One of the most fascinating aspects of axions is their ability to bridge several areas of physics that were previously thought to be disconnected. For instance, axions could potentially help reconcile two major challenges in modern physics: the discrepancy between quantum mechanics and general relativity, and the persistent mystery of dark matter. These two pillars of physics, quantum mechanics governing the behavior of particles at the smallest scales, and general relativity describing the forces at work in massive objects like stars and galaxies, have been difficult to integrate into a single theory. The introduction of axions into this conversation could provide the key to unlocking a unified understanding of both. The idea of axions was first proposed in the late 1970s as part of a solution to a problem in particle physics known as the strong CP problem. This problem arises from the fact that the laws of quantum chromodynamics, QCD, which describe the strong nuclear force that binds quarks together inside protons and neutrons, do not seem to allow certain types of symmetry violations, specifically CP symmetry violation, which refers to the breaking of combined charge conjugation and parity symmetry. In simple terms, this means that the universe should exhibit an equal amount of matter and antimatter, yet we observe an overwhelming abundance of matter. This discrepancy, known as the strong CP problem, needed to be addressed for the standard model of particle physics to be complete. Enter the axion. In an attempt to resolve this issue, theoretical physicists Roberto Pecchi and Helen Quinn proposed a new type of particle that could serve as a solution to the strong CP problem. This particle, which they called the axion, would have the property of spontaneously breaking the CP symmetry, thus providing an explanation for the apparent imbalance between matter and antimatter. While the axion's role in the strong CP problem has become an established aspect of theoretical physics, its connection to dark matter emerged more recently, as scientists began to realize that axions could also serve as a candidate for the elusive dark matter. The theoretical properties of axions make them uniquely suited for this role. First and foremost, axions are predicted to be extremely light, far lighter than any known particle, and yet incredibly abundant. Their small mass means that they could be produced in large quantities in the early universe, and as the universe expanded and cooled, these axions would have remained in a low-energy state, potentially forming a cold, dark matter component that could account for the observed gravitational effects we attribute to dark matter. Unlike traditional particles that interact through the electromagnetic force, axions interact primarily through the weak force and gravity, making them exceedingly difficult to detect but also giving them the potential to explain the gravitational effects that scientists observe in galaxies and clusters of galaxies. But how can scientists possibly detect such a particle? This is where the ingenuity of the scientific community comes into play. Over the past few decades, researchers have developed a variety of experimental strategies to detect axions, even though their weak interactions make them nearly impossible to observe directly. One promising approach is the use of large magnetic fields to convert axions into photons, particles of light, through a process known as the axion-photon coupling. If axions exist and if they interact with photons in this way, it may be possible to detect faint light signals emitted from axion sources, such as the cosmic background or near astrophysical objects like black holes or neutron stars. One such experiment, known as the Axion Dark Matter Experiment, ADMEX, is based at the University of Washington. This experiment uses a powerful magnetic field and a microwave cavity to detect the faint signals that could indicate the presence of axions. The sensitivity of ADMEX is continuously improving, as researchers refine their techniques and increase the precision of their instruments. Though axions have not yet been detected by ADMEX, the experiment has set stringent limits on their properties, narrowing down the possible mass range of axions and refining our understanding of the dark matter they may represent. Another experimental approach that has gained traction is the use of resonant cavities. In this method, researchers use resonant cavities, essentially chambers that resonate with specific frequencies of electromagnetic radiation, to try to detect the signals that would be produced if axions interact with magnetic fields. This technique, called the cavity haloscope, has been used in several recent experiments, including the CERN Axion Solar Telescope, CAST, and the Haystack experiment in the United States. These experiments also work by placing strong magnetic fields within the cavities and measuring any resulting electromagnetic signals that could be indicative of axion-photon interactions. Meanwhile, astronomers are using more traditional tools like telescopes to search for indirect signs of axions. While direct detection of axions is a formidable challenge, their effects might still be visible in cosmic phenomena. One of the most compelling indirect observations involves the study of the cosmic microwave background, CMB. The CMB is the afterglow of the Big Bang, and its properties can provide valuable insights into the conditions of the early universe. Axions, if they were present in the early universe, could have influenced the CMB in subtle ways, leaving behind distinct imprints that could be detected by sensitive instruments, like the Planck satellite. Another promising area of research involves the observation of neutron stars, specifically the phenomenon of pulsar timing. Pulsars are rotating neutron stars that emit regular pulses of radio waves, and any anomalies in the timing of these pulses could indicate the presence of axions. If axions are produced in the extreme environments of neutron stars, their presence could subtly alter the emitted radiation, providing a potential signature that scientists could measure. Even beyond our own universe, axions could hold the key to understanding phenomena such as the behavior of black holes. The presence of axions near the event horizon of a black hole might influence the emission of X-rays or other forms of radiation, creating subtle but detectable signals. This opens up the tantalizing possibility that axions might not only explain dark matter but also reveal new insights into the nature of black holes and the fundamental forces of the universe. At the same time, we must acknowledge that axions are only one potential solution to the dark matter problem. While they are an intriguing candidate, they are by no means the only one. Other dark matter candidates, such as weakly interacting massive particles, WIMPs, or sterile neutrinos, continue to be studied alongside axions. The fact that axions have not yet been detected does not mean that the search is futile. Rather, it reflects the enormity of the task at hand. As our detection methods improve and our understanding of the fundamental laws of physics deepens, the mystery of dark matter may eventually be solved, whether through the discovery of axions or some other, as yet undiscovered particle. Yet, regardless of which theory ultimately proves correct, the search for axions has already had a profound impact on science. It has spurred innovations in particle detection technologies, reshaped our understanding of the early universe, and provided new tools for exploring the very fabric of reality. The axion hypothesis represents the cutting edge of our attempt to understand the universe on the most fundamental level, combining the mysteries of quantum mechanics, particle physics, and cosmology into one unified framework. As we continue our journey into the unknown, the pursuit of axions reminds us that there are still vast expanses of knowledge left to explore. The nature of dark matter, the fundamental forces of the universe, and the origins of the cosmos itself are all questions that remain to be answered. With each new discovery, we move closer to a deeper understanding of the universe's mysteries, and axions, whether or not they are the answer to the dark matter enigma, are sure to remain a significant part of the ongoing adventure. As we continue exploring the potential of axions to unravel the mysteries of dark matter, it's essential to consider the broader implications that such a discovery could have on our understanding of the universe. Axions, though still hypothetical, represent a key piece of the puzzle and one of the greatest unsolved questions in modern physics. If they are indeed discovered, they will not only confirm dark matter's existence, but will also provide new insights into the fundamental forces that govern the universe. One of the profound consequences of discovering axions would be the impact on the standard model of particle physics. The standard model has served as the backbone of particle physics for decades, providing us with an accurate description of the fundamental particles and forces in the universe. However, it has its limitations. The existence of dark matter, as well as the unexplained properties of gravity at cosmic scales, has pointed to the need for an extension to the standard model. Axions could play a central role in this extension, potentially leading to a new understanding of both particle physics and cosmology. Their discovery might not only clarify the nature of dark matter but could also shed light on other mysteries, such as the nature of neutrinos and the mechanism of gravity itself. Beyond the implications for particle physics, the discovery of axions could also have a transformative impact on our understanding of the early universe. The role of axions in the formation of dark matter suggests that they could have been produced in large quantities during the Big Bang, helping to shape the universe as we know it. By studying the properties of axions and their interactions with other particles, scientists could learn more about the conditions of the early universe, including the processes that occurred within the first few moments after the Big Bang. This could provide valuable insights into the evolution of galaxies, stars, and other cosmic structures, helping to refine our models of cosmic history. One particularly exciting area of research involves the study of axions in the context of cosmological inflation. Inflation is a theory that suggests that the universe underwent a rapid expansion in the moments following the Big Bang, and it is thought to have played a crucial role in shaping the large-scale structure of the universe. Axions, with their predicted abundance and interactions, could have been a key player in the inflationary epoch, potentially influencing the distribution of matter and the formation of the cosmic structures we observe today. By studying the relationship between axions and inflation, scientists could gain new insights into the very origins of the universe itself. Another intriguing possibility is that axions could help resolve some of the long-standing mysteries surrounding the nature of the forces of gravity and electromagnetism. The theory of axions suggests that they could interact with both electromagnetic fields and the weak nuclear force, which could lead to new insights into how these forces behave at both the microscopic and macroscopic scales. If axions are found to have properties that affect the way light propagates through space or influence the gravitational fields around massive objects like black holes, it could force physicists to rethink their current models of the fundamental forces. While axions have the potential to revolutionize our understanding of physics, the quest to detect them is no easy task. The fact that axions interact so weakly with other particles means that they are incredibly difficult to detect. Current experiments, like ADMEX, are pushing the limits of sensitivity, but the search for axions is still very much in its early stages. Researchers are exploring a variety of different techniques to detect these elusive particles, from microwave cavities to resonant cavities and beyond. Each of these methods has its strengths and challenges, and as the technology behind these experiments continues to improve, the chances of detecting axions are gradually increasing. One of the most exciting developments in this area is the use of advanced quantum technologies to improve the sensitivity of axion detection experiments. Quantum sensors, which take advantage of the principles of quantum mechanics to measure extremely small changes in physical quantities, have the potential to vastly improve the precision with which we can detect axions. These sensors could allow scientists to detect even the faintest signals from axions, opening up new possibilities for discovery. As quantum technologies continue to advance, they could play a pivotal role in the search for dark matter and the detection of axions. In addition to their potential as dark matter candidates, axions also have intriguing implications for our understanding of particle physics beyond the standard model. The search for axions is intrinsically linked to the broader quest for new particles and forces that could expand our knowledge of the universe. Over the past few decades, physicists have increasingly recognized the need for theories that go beyond the standard model, and axions could be one of the key components of these theories. As we continue to probe the nature of dark matter and the fundamental forces of the universe, the discovery of axions would represent a major breakthrough in our search for a more complete theory of the cosmos. At the same time, we must also recognize that axions are far from the only theoretical candidate for dark matter. While they have gained significant attention in recent years, other particles, such as WIMPs, weakly interacting massive particles, continue to be studied as potential dark matter candidates. Each of these theories offers a different perspective on the nature of dark matter, and the challenge for scientists is to determine which of these candidates, if any, is correct. The search for axions is part of this broader effort to uncover the true nature of dark matter and its role in the universe. As researchers continue to explore the potential of axions, we can expect to see new developments in both theoretical physics and experimental technology. Advances in particle detectors, as well as the development of new theoretical models, will continue to push the boundaries of what we know about the universe. Whether or not axions turn out to be the key to understanding dark matter, their study is already providing us with valuable insights into the fundamental laws of physics and the nature of the universe. As we look to the future, the search for axions and other dark matter candidates will likely remain one of the most exciting areas of scientific inquiry. The implications of a discovery, whether it be axions or some other particle, are immense. If axions are detected, they will not only provide an answer to one of the greatest mysteries in modern science but will also open up new frontiers in our understanding of the universe. From the nature of dark matter to the evolution of the cosmos, the discovery of axions could have profound implications for everything we know about the universe and the laws that govern it. Axions represent one of the most promising and intriguing theoretical candidates for explaining dark matter and providing insights into some of the deepest mysteries of the universe. Despite being hypothetical particles, their potential to resolve the dark matter enigma, reconcile quantum mechanics with general relativity, and unlock new knowledge about the early universe makes them a key focus of modern physics research. The search for axions is far from over, and as new technologies and experiments continue to evolve, the hope of discovering these ghostly particles grows ever stronger. Whether axions are ultimately found or not, their study is an important step in the ongoing quest to understand the universe on the most fundamental level. The journey into the unknown continues, and the pursuit of axions may very well lead us to the answers we seek. As we continue exploring the theoretical landscape of axions and their potential to solve the mystery of dark matter, it's worth diving deeper into how their properties might connect with other unresolved problems in physics. Axions not only stand at the frontier of dark matter research, but they may also hold the key to understanding a variety of phenomena in the universe that remain elusive. Let's take a closer look at how the discovery of axions could link different areas of physics, and how their existence might alter our perception of reality. One area where axions have significant potential is in the study of the strong force and quantum chromodynamics, QCD, the theory that describes how quarks and gluons interact. The theory of axions originally emerged from an attempt to solve the strong CP problem in QCD. The strong CP problem refers to the puzzling absence of certain symmetry violations that would be expected in the strong interaction, which binds protons and neutrons together in atomic nuclei. In theory, the strong force should allow for the violation of a symmetry known as CP symmetry, the symmetry between particles and their mirror image counterparts. But experiments have shown that this violation is practically non-existent. This presents a major conundrum in our understanding of the strong interaction. In the 1970s, physicist Roberto Pecchiai and his collaborator Helen Quinn proposed that the solution to this problem could lie in the existence of a new particle, the axion. This was because the axion's very nature would allow it to dynamically cancel out CP violation in a way that aligns with observed physical phenomena. Essentially, the axion provides an elegant solution to this outstanding issue in particle physics. While the direct connection between axions and the strong CP problem might seem abstract at first glance, it demonstrates just how deeply entwined axions are with the fundamental forces that govern particle interactions. Furthermore, Axion's potential connection to both dark matter and the strong CP problem means they are positioned at the intersection of cosmology, quantum field theory, and high-energy physics. This central positioning opens the door for a unified framework that can explain the behavior of dark matter and other fundamental forces in a single theory. Such a framework could potentially extend our understanding of the universe far beyond what current models allow. As we've touched on, axions are extremely difficult to detect due to their weak interactions with other particles. However, the methods being developed to capture their elusive signatures are pushing the boundaries of modern technology. As mentioned before, experiments like the Axion Dark Matter Experiment, ADMEX, are at the forefront of the search for axions. ADMEX utilizes a technique called a resonant cavity to detect the extremely faint electromagnetic signals that axions might produce when they interact with strong magnetic fields. While the sensitivity of current experiments is impressive, axion detection remains a major technological challenge. This is where recent advances in quantum mechanics and quantum computing have the potential to revolutionize the way we approach dark matter detection. Quantum sensors, which rely on the weird properties of quantum mechanics like superposition and entanglement, could allow us to measure incredibly small signals, potentially making it possible to spot axions that are otherwise indistinguishable from background noise. In the next few decades, quantum technologies could dramatically enhance the sensitivity of axion searches, possibly leading to groundbreaking discoveries. The importance of axion research extends beyond just solving the dark matter problem. Their potential to revolutionize our understanding of particle physics means that the discovery of axions would likely lead to new insights in a wide variety of areas. For instance, axions may also be related to the behavior of neutron stars, the incredibly dense remnants of massive stars that have exploded as supernovae. Neutron stars are known to exhibit extreme magnetic fields, and if axions interact with these fields, it could provide new information about their internal structure and dynamics. Moreover, axions could even play a role in explaining some of the more bizarre phenomena observed in cosmology, such as the mysterious acceleration of the expansion of the universe. This acceleration, attributed to a force called dark energy, is one of the most puzzling aspects of modern cosmology. Some researchers have speculated that axions might help explain the nature of dark energy by providing a mechanism through which vacuum energy could be converted into dark energy. This would further link axions with dark matter and the broader cosmological picture. Additionally, axions are not only being considered as candidates for dark matter but are also being explored in the context of high-energy physics. If axions were to interact with other particles in unexpected ways, they could offer new avenues for research into particle accelerators, such as the Large Hadron Collider, LHC. The LHC has already helped identify the Higgs boson, the particle responsible for giving other particles mass, but axions could reveal new phenomena beyond the Higgs mechanism. In fact, experiments that look for signs of axions in particle accelerators could help us uncover particles or forces that we haven't even imagined yet. On a more philosophical level, the discovery of axions could also challenge our understanding of the very nature of reality itself. For centuries, physicists have sought to unify the different fundamental forces, gravity, electromagnetism, the strong nuclear force, and the weak nuclear force, into a single theory. Known as the theory of everything (TOE), this theory would explain all the forces of nature in one comprehensive framework. Axions, with their unique properties and potential to connect dark matter to the strong force, might be a critical component in this unification process. Their discovery would not only revolutionize particle physics, but could also lead to a major paradigm shift in how we view the universe at the most fundamental level. The excitement around axions is not just limited to theoretical physicists. As their possible existence continues to be explored in laboratories and observatories across the world, axions have captured the imagination of the public and science enthusiasts alike. The idea that a particle so small and so elusive could hold the key to understanding dark matter, and perhaps even the origins of the universe, is an inspiring thought. It fuels the sense of wonder and curiosity that has driven humanity's pursuit of knowledge for centuries. In the coming years, the global scientific community will continue to work together to test the hypothesis of axions. The search for dark matter remains one of the most pressing challenges in modern science, and axions are at the heart of this quest. Whether or not they turn out to be the answer, the investigation of axions will surely advance our understanding of the universe in ways we cannot yet fully comprehend. As the search for axions progresses, it will be crucial for scientists to continue exploring other dark matter candidates as well. While axions are one of the most promising possibilities, the nature of dark matter may ultimately turn out to be even stranger and more complex than we could have imagined. Nevertheless, the journey to understanding dark matter will undoubtedly lead to new discoveries in physics and cosmology, and axions will likely remain a key player in this ongoing adventure. The search for axions is more than just a scientific pursuit. It is a journey that connects us to the deepest questions of existence. What is dark matter? How does the universe work at its most fundamental level? What are the limits of human knowledge? The discovery of axions, if it happens, would not only solve the dark matter mystery but would also open up new avenues for exploration, sparking new questions and possibilities about the very nature of reality. And perhaps, just as importantly, it would remind us that the pursuit of knowledge is an unending journey, one that continues to push the boundaries of what we know and how we see the universe. As we continue the discussion surrounding axions and their potential to solve the mystery of dark matter, it's essential to examine how the search for these elusive particles intersects with ongoing advancements in technology and the broader landscape of physics research. We're on the edge of a scientific frontier where discoveries in fundamental physics could reshape our understanding of the universe in profound ways. But how will we actually detect axions? The journey ahead involves sophisticated techniques, experimental ingenuity, and the global collaboration of scientists pushing the boundaries of current technology. For years, experiments like the Axion Dark Matter Experiment, ADMEX, and the CERN Axion Solar Telescope, CAST, have been at the forefront of the search for axions. ADMEX, for example, operates by using a strong magnetic field to convert axions into microwave photons, which can then be detected. This method relies on the axion's ability to interact with photons in a way that would generate detectable signals. The setup of ADMEX is remarkable in its sensitivity, utilizing resonant cavities to amplify the signal from axions, which might otherwise be undetectable amidst the background noise of other cosmic radiation. The innovative designs behind experiments like ADMEX represent the cutting edge of experimental physics. They involve the careful tuning of resonant frequencies and the creation of ultra-sensitive detectors, all working together to identify the faintest of signals. Yet, despite the sensitivity of these detectors, axion detection remains elusive. This is partly due to the very weak interactions of axions with other matter, which makes them extraordinarily difficult to detect. Even though axions are theorized to make up the majority of dark matter in the universe, proving their existence could take decades, if not longer. There is also the issue of axion mass. The mass of axions is still unknown, but theoretical models suggest that they are extremely lightweight, possibly much lighter than even the neutrinos. Their incredibly small mass is one reason they would not be detectable by conventional means. In fact, much of the current experimental design is focused on identifying the faintest signals, meaning scientists are working to improve the precision of axion mass measurements. If axions turn out to be much lighter than current estimates, it would require entirely new techniques and equipment to detect them. On the other hand, if axions are heavier than expected, they may reveal themselves through their interactions with other particles, opening the door to new avenues of discovery. Another promising approach involves the use of optical experiments. In these experiments, scientists hope to detect axions by observing their potential to interact with photons in magnetic fields. Known as the axion-photon interaction, this theoretical process suggests that axions could convert into high-energy photons when placed under strong magnetic fields, producing detectable electromagnetic signals. One such experiment is the helioscope method, which focuses on axions that may be produced in the Sun's core. The CAST experiment, based at CERN, uses this method to attempt the detection of solar axions that could be emanating from the Sun. What makes these experiments so fascinating is that they are pushing the limits of our technological capabilities. Detecting axions would require the use of extremely sensitive equipment, capable of measuring incredibly small variations in energy and magnetic fields. In many ways, axion detection is a race against time and technology, as the sensitivity of detectors must be continually refined to overcome the sheer elusiveness of these particles. In the quest to detect axions, the role of international collaboration cannot be overstated. Researchers around the world are working together to share ideas, experiment with new techniques, and combine their findings in ways that no single laboratory could achieve alone. The search for axions, much like the search for dark matter itself, is a global effort. The pooling of resources, expertise, and technological know-how increases the likelihood of success. This spirit of collaboration is essential in tackling some of the most challenging problems in physics. Given the immense complexity and scale of the questions at hand, solving the mystery of dark matter will undoubtedly require the combined effort of scientists from multiple disciplines. In parallel with these experimental efforts, advances in theoretical physics are also making a significant impact. As new mathematical models are developed, researchers are refining our understanding of the potential properties of axions and how they might interact with other particles. For example, researchers have been investigating the potential role of axions in the early universe. If axions were present during the formation of the universe, they could have played a crucial role in shaping the cosmic landscape. Theories suggest that axions could have influenced the distribution of matter in the early universe, potentially explaining the observed large-scale structure of the cosmos. Another exciting avenue of research involves axions' potential connection to gravitational waves. Gravitational waves, which are ripples in the fabric of spacetime caused by massive objects like black holes or neutron stars, have been a major focus of scientific exploration. However, the interaction between axions and gravitational waves remains largely unexplored. If axions were present in the early universe, their interactions with gravitational waves could leave an imprint on the cosmic microwave background (CMB) radiation. Detecting these subtle imprints would require highly sensitive equipment and a deep understanding of how axions could influence the propagation of gravitational waves. In a broader sense, axions could also provide a new lens through which to study the physics of the early universe. Theoretical physicists are working to integrate the concept of axions into the broader framework of cosmology and the standard model of particle physics. If axions do exist and are a significant component of dark matter, they could hold the key to unlocking a new understanding of the universe's origins. This would open up entirely new areas of inquiry, as scientists would need to reconsider established theories of cosmology, quantum mechanics, and high-energy physics. Despite the promising theoretical framework for axions, there are still many unknowns. The possibility that axions could form part of the mysterious dark matter that fills the cosmos adds another layer of intrigue. Since dark matter cannot be directly observed, scientists must rely on indirect evidence, such as the gravitational effects it has on visible matter. If axions are indeed dark matter, their faint presence could help explain a wide range of cosmic phenomena, from the rotation curves of galaxies to the formation of large-scale cosmic structures. For those interested in the history of science, the discovery of axions could be a milestone akin to the discovery of the Higgs boson. Just as the Higgs boson was a long-sought particle whose existence was postulated by theoretical physicists, axions represent another great theoretical prediction that could transform our understanding of the universe. If axions are discovered, it would be a breakthrough not only in dark matter research but in the entire field of particle physics. The implications of such a discovery are enormous. It would not only resolve one of the most pressing mysteries in cosmology but could also lead to the development of new technologies and a deeper understanding of the fundamental forces that govern the universe. Moreover, it would signify a major shift in how we approach problems in physics, demonstrating that the quest for knowledge is still very much alive and that many of the universe's most profound secrets remain hidden just beyond our reach. Axions are a tantalizing possibility in the search for dark matter. Their discovery would have far-reaching consequences for our understanding of both the quantum world and the cosmos. As we continue to explore the frontiers of physics, the search for axions reminds us of the deep mysteries that still await us. Perhaps, in the years to come, the elusive axion will be found, illuminating dark matter and rewriting the fundamental laws of physics in ways we cannot yet imagine. And with it, a new chapter in the story of the universe will unfold, one where the invisible forces that shape reality are finally brought to light. As we continue to dive deeper into the potential of axions and their role in solving the dark matter puzzle, it's important to emphasize how their discovery could impact more than just our understanding of the cosmos. The implications of detecting axions go far beyond simply confirming the existence of dark matter. They could change the very way we think about the universe's fundamental building blocks. Just as the discovery of the Higgs boson opened new doors to understanding mass and the forces that shape our universe, axions could similarly lead to profound revelations about the nature of matter, energy, and the very fabric of space-time itself. To grasp the significance of axions, it's essential to understand the broader context of their potential discovery. Dark matter, which makes up about 27% of the universe's total mass energy content, has been a source of speculation and debate for nearly a century. While we can observe the gravitational effects of dark matter on galaxies, clusters of galaxies, and the cosmic microwave background radiation, we still know very little about its actual composition. It doesn't interact with light or any of the electromagnetic forces, making it invisible to direct detection using traditional telescopes or particle detectors. This is where axions come in. If they exist, they could provide the missing link in our understanding of dark matter. The key reason axions are a leading candidate for dark matter is their theoretical properties. They are predicted to have a very low mass, meaning they could populate the universe in vast quantities. Furthermore, axions are postulated to have interactions with photons, light particles, that, although incredibly weak, could still be detectable using cutting-edge technologies like the ones used in the Axion Dark Matter Experiment, ADMEX, and other ongoing axion research projects. The ability to detect axions would represent a monumental leap forward in experimental physics. The instruments currently being developed and used to search for axions are pushing the limits of what we thought possible. For example, ADMEX uses a superconducting magnet and a special cavity resonator to enhance the potential for detecting axion-induced photons. The concept behind this setup is simple yet brilliant. Axions passing through the strong magnetic field are expected to convert into detectable photons under certain conditions. The search for these faint signals has required the development of highly sensitive detectors, as even a tiny signal could hold the key to confirming axions as dark matter candidates. The sensitivity of such experiments has been steadily improving, thanks in part to innovations in quantum technology and advances in materials science. In particular, the development of ultra-low noise amplifiers and superconducting detectors has enabled researchers to push the sensitivity of their instruments to levels that were previously unimaginable. This progress brings us closer to a breakthrough, where we might finally detect the elusive axions and unlock a new understanding of dark matter. Beyond detecting axions, the discovery of these particles could lead to new insights into the fundamental nature of physics. If axions are confirmed as dark matter, they could offer a window into physics beyond the Standard Model. The Standard Model, which describes the electromagnetic, weak, and strong nuclear forces, has been incredibly successful in explaining much of the behavior of elementary particles. However, it leaves many questions unanswered, most notably, the nature of dark matter, which is a critical component of the universe's structure. Axions, being a potential component of dark matter, could be the first direct evidence of new physics beyond the Standard Model. In addition, axions might help to resolve another great mystery in modern physics, the matter-antimatter asymmetry of the universe. According to current understanding, the Big Bang should have produced equal amounts of matter and antimatter. However, we observe a universe predominantly made of matter, with only trace amounts of antimatter. One theory suggests that axions could have played a role in this imbalance. If axions were present in the early universe, they could have contributed to processes that favored the production of matter over antimatter, thus explaining why we observe more matter today. On a more speculative note, axions may also help to unify the fundamental forces of nature. Physicists have long sought a theory of everything, a single framework that can explain all fundamental forces, including gravity, electromagnetism, and the nuclear forces. The discovery of axions could contribute to this quest, particularly if their interactions reveal hidden symmetries or connections between different forces. If axions turn out to be tied to forces beyond those described by the Standard Model, they could potentially serve as a bridge to a deeper, more unified theory of physics. However, even as research into axions progresses, challenges remain. Despite the theoretical promise of axions, detecting them is no easy feat. The weak interactions of axions with other matter make them incredibly difficult to spot. Unlike more familiar particles like electrons or protons, which interact strongly with electromagnetic fields, axions interact only very weakly. This weak interaction is both a strength and a limitation. While it makes axions a promising candidate for dark matter, it also means that they are extremely difficult to detect in the lab. There are also competing theories about dark matter that must be considered. While axions are one of the leading candidates, other possibilities, such as weakly interacting massive particles, WIMPs, and sterile neutrinos, remain viable. The search for dark matter is ongoing, and the discovery of axions could be just one part of a much larger puzzle. The presence of axions would provide a significant piece of evidence in favor of certain models of dark matter, but it wouldn't necessarily rule out other possibilities. Moreover, axions are just one of many theoretical particles that could explain dark matter. Other hypothetical particles, such as WIMPs, also possess many of the properties that make them attractive candidates for dark matter. WIMPs, for instance, would have a much higher mass than axions and would interact more strongly with ordinary matter. The search for WIMPs is equally intense, with experiments like the Large Hadron Collider, LHC, and the Xenon Dark Matter Detector all looking for signs of these elusive particles. The competition between axion detection and the search for WIMPs is one of the most exciting aspects of modern particle physics, as both could offer groundbreaking insights into the mysteries of the universe. Another factor to consider is the potential for new discoveries in related fields. The detection of axions could lead to advancements in quantum technology, with applications in fields ranging from computing to telecommunications. Quantum computers, for instance, rely on the principles of quantum mechanics to solve problems that are currently beyond the reach of classical computers. If axions play a role in quantum processes, their discovery could have a profound impact on the development of quantum technologies. The future of axion research looks promising, but there are still many obstacles to overcome. As more advanced experiments are conducted and our understanding of the universe deepens, it's likely that the role of axions in dark matter will become clearer. The search for these ghostly particles will continue to push the boundaries of experimental physics, and with each step forward, we move closer to unraveling one of the greatest mysteries of the cosmos. Axions represent a tantalizing possibility in the quest to understand dark matter. Their discovery could have far-reaching implications, not only for our understanding of the universe but also for the future of fundamental physics. As scientists continue to push the limits of technology and theory, the search for axions will undoubtedly remain at the forefront of physics research. Whether or not axions are the key to unlocking the mystery of dark matter, their potential to revolutionize our understanding of the cosmos makes them one of the most exciting areas of scientific exploration today. As we continue our journey into the realm of axions, it's crucial to understand the broader implications their discovery could have on the scientific community and the world at large. If axions turn out to be the elusive dark matter particles that scientists have been searching for, it could mark the beginning of a new era in physics. It would not only validate a specific theory about the makeup of the universe but also open up new frontiers for discovery. This kind of breakthrough could inspire a new generation of scientists and thinkers, revolutionizing our technological landscape and even how we approach space exploration. Theoretical work around axions is not just confined to dark matter. Their existence could provide answers to some of the most profound questions in physics. One such question is the nature of the strong nuclear force. The strong force is one of the fundamental forces of nature, holding atomic nuclei together. However, this force is not fully understood. Axions could provide insight into the complexities of this force, especially in its interactions with other types of matter and energy. Axions could also shed light on the origins of the universe itself. The way axions interact with photons and other particles might reveal more about the events that transpired during the earliest moments of the Big Bang. Their existence could even offer insight into the nature of cosmic inflation, the rapid expansion of the universe in the moments after the Big Bang, a process that is still poorly understood. Understanding axions could potentially lead to breakthroughs in these areas, providing us with a more complete picture of the universe's origins. Axions' potential connection to other mysterious cosmic phenomena is another intriguing aspect that scientists are actively exploring. For instance, it is theorized that axions might be involved in the creation of some of the most enigmatic features of the universe: dark energy. Dark energy, which makes up about 68% of the universe's total energy content, is responsible for the accelerated expansion of the universe. Like dark matter, dark energy has remained elusive, with little direct evidence supporting its existence. If axions are indeed tied to dark matter, they might also play a role in dark energy's mysterious effects. Another fascinating possibility is that axions could be responsible for certain cosmic anomalies, such as the behavior of galactic rotation curves. Observations of galaxies show that the outer stars are rotating much faster than would be expected based on the visible matter alone. This has led to the hypothesis that there is some unseen mass, dark matter, acting as a kind of gravitational glue to hold galaxies together. Axions, being a candidate for dark matter, could explain these unusual rotation patterns. If their presence were confirmed, it would provide a major piece of the puzzle in our understanding of galactic dynamics. The idea of axions influencing the very structure of space-time is also being actively explored. According to certain models of physics, axions could contribute to the formation of cosmic structures like galaxies and galaxy clusters. This connection between axions and cosmic evolution could reshape our understanding of how the universe's large-scale structure came to be. It could reveal a new connection between particle physics and cosmology, potentially leading to a more unified theory of physics. One of the most exciting prospects of axion research lies in its ability to bridge the gap between two seemingly incompatible areas of physics: quantum mechanics and general relativity. These two theories, which describe the behavior of particles on very small scales, quantum mechanics, and the behavior of gravity on large scales, general relativity, have thus far resisted any attempts to unify them. Axions, with their potential role in both cosmological phenomena and quantum processes, could serve as a crucial link between these two areas. If axions are confirmed to exist, they might provide a pathway toward the long-sought theory of everything, which would explain all the fundamental forces in the universe within a single, cohesive framework. The potential for practical applications arising from axion research is another exciting aspect. While it may seem far-fetched to think of these ghostly particles leading to tangible technological advancements, the history of science has shown us that breakthroughs in fundamental physics often lead to unexpected innovations. For example, the discovery of the electron, once thought to be an abstract concept, has paved the way for everything from semiconductors to computers to modern telecommunications. Similarly, the discovery of axions could open up new possibilities in areas like energy production, quantum computing, and even gravitational wave detection. The search for axions also has an impact on other fields of science, including astrophysics and space exploration. Understanding dark matter and its components, like axions, could help us better understand the structure and behavior of galaxies, stars, and other cosmic bodies. This could eventually lead to more accurate models for predicting the evolution of the universe and the future of galaxies, including our own Milky Way. It could also influence the design and planning of space missions, particularly those aimed at studying the cosmic microwave background radiation and other features of the universe that are influenced by dark matter. While the scientific community is still grappling with how to detect and confirm axions, the progress made so far is encouraging. As detection techniques continue to improve and more experimental data becomes available, the possibility of axions becoming a key part of our understanding of the universe grows more likely. The instruments and technologies being developed to search for axions are pushing the boundaries of modern physics. For example, the use of highly sensitive microwave cavities in experiments like ADMEX is an innovative approach that could dramatically improve the chances of detecting axions. These advancements in technology are not only exciting for axion research, but also for the broader field of particle physics. The potential discovery of axions could also have philosophical implications. If these particles are found to be the key to understanding dark matter, it could challenge our very perception of reality. For centuries, scientists and philosophers have pondered the nature of existence and the universe's fundamental forces. The discovery of axions could offer a new lens through which to view the cosmos, potentially changing how we think about space, time, and the nature of matter itself. It could inspire a new wave of philosophical inquiry into the meaning of the universe, bringing together science and philosophy in ways that we haven't yet imagined. Despite all the excitement surrounding axions, there are still many challenges ahead. While the theoretical framework for axions is well established, experimental confirmation remains elusive. This is due to the extremely weak interactions that axions have with ordinary matter. Unlike other particles that we can observe directly in particle detectors or through their effects on other particles, axions require incredibly sensitive instruments to detect even the faintest signals. The search for axions is a delicate, painstaking process that demands both creativity and patience. However, as our understanding of axion physics continues to grow, we are becoming better equipped to detect these particles and unlock their mysteries. Axions represent one of the most promising and fascinating avenues of research in modern physics. Their potential to explain dark matter, bridge gaps between quantum mechanics and general relativity, and unlock new technologies is truly exciting. The search for axions is not just about solving one of the most profound mysteries of the universe. It's about transforming our understanding of the very fabric of reality itself. With each new breakthrough in axion research, we move closer to uncovering the truth about dark matter, the origins of the universe, and the nature of the fundamental forces that govern our existence. As we continue to probe the mysteries of the cosmos, axions remain one of the most intriguing and elusive candidates for explaining the universe's deepest secrets. Whether or not they are the key to dark matter, the ongoing search for axions promises to expand the boundaries of science and inspire new generations of thinkers to explore the unknown. And in doing so, we may uncover not just the nature of dark matter, but also new realms of understanding that will shape the future of physics for years to come. As the search for axions continues, scientists are also exploring new, more advanced methods for detecting these elusive particles. One of the most innovative techniques is known as the rotating cavity method. This approach aims to increase sensitivity by using a superconducting magnet to generate a strong magnetic field in a rotating cavity, which in turn could help produce detectable signals from axions. By rotating the cavity, researchers hope to maximize the chance that axions interact with electromagnetic fields, thus making them more detectable. While this method is still in its experimental stages, it represents a leap forward in the technology and creativity needed to unlock the secrets of axions. Another promising technique is the use of laser interferometry to detect axions. Laser interferometers work by measuring tiny changes in the interference pattern of light as it passes through a system of mirrors. The idea is that axions, as they pass through space, could subtly affect the path of light in a way that could be detected by a laser interferometer. This method is particularly exciting because it could be used to measure axions that might be present in the magnetic fields surrounding Earth or even from distant regions of space. At the same time, there are more traditional methods being used to search for axions. One of the most notable is the Axion Dark Matter Experiment, ADMEX, which is currently one of the most sensitive and advanced detectors designed to catch a glimpse of axions. ADMEX is based on the concept that axions, as they interact with magnetic fields, could convert into photons, particles of light. By looking for these rare and faint photons, scientists hope to directly detect axions for the first time. ADMEX has been continuously improving its sensitivity, and could potentially lead to a breakthrough in the next few years. If successful, it would not only revolutionize our understanding of dark matter but also provide an entirely new window into the mysterious nature of the universe. The role of axions in astrophysics is also a major focus of ongoing research. If axions do make up dark matter, they would have profound implications for our understanding of the structure and evolution of the universe. For instance, the presence of axions could explain some of the anomalies observed in the cosmic microwave background radiation, the afterglow of the Big Bang. This radiation carries vital information about the early universe, and the detection of axions could provide new insights into the conditions that prevailed in the first few moments after the Big Bang. Axions could also offer a fresh perspective on the formation of galaxies. Observations of galactic rotation curves have long puzzled astronomers, as the outer edges of galaxies are observed to rotate much faster than would be expected if only visible matter were present. This discrepancy has been attributed to the presence of dark matter, but its exact nature remains unclear. If axions are responsible for this invisible matter, their detection could not only explain this galactic behavior but also lead to a deeper understanding of the role dark matter plays in the formation of large-scale structures in the universe. The gravitational effects of axions might help to shape the way galaxies evolve, providing a more complete picture of cosmic history. In addition to their potential connection to dark matter, axions are also considered prime candidates to help explain another mysterious phenomenon, the matter-antimatter imbalance in the universe. According to the standard model of particle physics, the Big Bang should have produced equal amounts of matter and antimatter. However, we observe an overwhelming dominance of matter in the universe today, with very little antimatter. This imbalance is one of the great unsolved mysteries in physics. Some theories suggest that axions, through a process called CP violation, could play a role in generating this asymmetry by favoring the creation of matter over antimatter during the early universe. If axions are indeed involved in this process, they could provide a crucial piece to the puzzle of why our universe is made mostly of matter. One of the other areas where axions could make an impact is in the study of cosmic inflation. This theory suggests that, in the moments immediately following the Big Bang, the universe expanded at an exponential rate. Understanding the forces behind this rapid expansion is a key challenge in modern cosmology. Some models propose that axions could have played a role in driving this inflationary period. Their interactions with other particles, including photons, could have influenced the expansion of the universe, potentially leaving imprints on the cosmic microwave background radiation. If we can detect signals from axions related to cosmic inflation, it could provide a powerful tool for probing the very beginnings of our universe. The search for axions has also spurred collaborations across international scientific communities, uniting researchers from diverse fields of study. For example, collaborations between particle physicists, cosmologists, and astronomers have led to a more integrated approach to understanding dark matter and axions. These cross-disciplinary partnerships are not only accelerating the pace of discovery, but are also creating a more holistic view of the universe's structure and the forces that govern it. This collaborative spirit exemplifies the power of scientific teamwork in tackling some of the most fundamental questions about the nature of the cosmos. If axions are ultimately discovered, they could open the door to a completely new branch of physics that explores the interactions between particles and forces that are currently beyond our understanding. The discovery of axions could prompt a reevaluation of the standard model of particle physics, and lead to the development of new theories to explain the forces and particles that govern the universe. In a sense, the hunt for axions is not just about solving one specific mystery. It's about fundamentally altering our understanding of how the universe works at the most basic level. While the discovery of axions is still theoretical, the ongoing research and the experiments designed to detect them are a testament to the spirit of scientific curiosity and innovation. Just as the discovery of the electron or the Higgs boson revolutionized our understanding of the universe, the discovery of axions could lead to a paradigm shift in the field of physics. The implications of such a discovery extend far beyond the confines of dark matter. They could influence everything from the nature of gravity to our understanding of the early universe, potentially answering questions that have puzzled humanity for centuries. The search for axions is an exciting chapter in the story of human exploration and scientific discovery. It represents the convergence of cutting-edge technology, bold new ideas, and the deep curiosity that drives scientists to push the boundaries of knowledge. Whether or not axions are the key to unlocking the mysteries of dark matter, their potential to reshape our understanding of the universe makes them one of the most intriguing phenomena in modern physics. As we continue to explore the cosmos, The search for axions is likely to play a central role in the next generation of scientific breakthroughs, challenging our assumptions and expanding our horizons in ways we can only begin to imagine. The discovery of axions, or any new particles that may be found through similar research, would be a monumental moment in the history of physics. It would confirm that our universe holds secrets still waiting to be uncovered, and that the more we explore, the more we realize just how little we truly understand about the fundamental nature of reality. And even if axions aren't the answer to every question, their discovery would be a testament to human ingenuity and the power of science to unravel the mysteries of the cosmos. The quest for axions is more than just a race to uncover dark matter. It's a deeper journey into understanding the very fabric of the universe. It's about connecting the dots between the microscopic and the cosmic. As scientists look for ways to detect axions, they are also pushing the limits of what we know about fundamental forces and particles. With each new experiment, each new theory, and each new piece of data, our understanding of the cosmos grows, and the search for axions becomes a key stepping stone in unlocking the universe's deepest secrets. One of the most exciting aspects of axion research is the potential to link quantum mechanics with general relativity. Quantum mechanics, the theory that governs the behavior of particles on the smallest scales, and general relativity, the theory that explains gravity and the behavior of large objects like planets and galaxies, are the two pillars of modern physics. However, these two theories have never been fully reconciled. They describe the universe in ways that are mathematically incompatible. If axions exist and play a significant role in dark matter, they could serve as a bridge between these two foundational theories. They might provide a way to link the microscopic world of particles with the macroscopic world of gravity, helping to form a unified theory of everything that physicists have long sought. The detection of axions could lead to groundbreaking discoveries not only in astrophysics, but also in the way we view space-time itself. Currently, our understanding of space-time is largely shaped by Einstein's theory of general relativity, which describes the curvature of space-time caused by mass and energy. However, axions, if detected, could help redefine how we perceive the universe's underlying structure. These ghostly particles, with their mysterious properties, could show that space-time behaves in ways we have never imagined. This could open up entirely new realms of physics, where concepts like gravity and quantum mechanics no longer exist in isolation but are instead woven together into a more comprehensive framework. While the search for axions is still ongoing, the potential rewards are immense. If we do detect axions, it would confirm the existence of dark matter and give us a new tool to study the universe on both the smallest and largest scales. The impact on cosmology would be profound, offering a new way to probe the structure of galaxies, clusters of galaxies, and even the formation of the universe itself. Axions could be the missing piece that explains how matter behaves in the vast stretches of space, and why the universe behaves the way it does. They could also provide new insights into the big questions of science, like why the universe is composed of more matter than antimatter, and how the fundamental forces interact with each other. The implications for particle physics are also profound. The discovery of axions would challenge the Standard Model, the current framework that describes the known particles and forces in the universe. While the Standard Model has been incredibly successful in explaining much of the physical world, it has limitations, particularly in its inability to account for dark matter, dark energy, and the mystery of gravity. Axions could help fill in the gaps in the Standard Model, providing answers to some of its most stubborn questions. This could lead to the development of new theories, new particles, and new ways of thinking about the universe. The search for axions also highlights the role of advanced technology in modern scientific discovery. Over the years, physicists have developed increasingly sophisticated tools to explore the universe, from particle accelerators like the Large Hadron Collider to telescopes that peer into distant galaxies. The experiments designed to detect axions are no exception. They require cutting-edge technology and innovative ideas to push the boundaries of what we can measure and observe. These technologies, in turn, drive advances in other fields, creating ripple effects that impact everything from medicine to materials science to engineering. The tools and techniques developed for axion research will undoubtedly have far-reaching applications beyond just the study of dark matter. In addition to their potential impact on physics, axions could also play a role in the development of new technologies. The search for dark matter and the exploration of axions has already led to advancements in detector technology, superconducting materials, and quantum computing. The techniques developed to detect axions, like laser interferometry and cavity-based detectors, could be applied to other areas of science and industry. In fact, many of the technologies that emerged from the study of particle physics, such as the World Wide Web and MRI machines, have already had a profound effect on our daily lives. The search for axions could be the next frontier in the ongoing technological revolution, leading to innovations that improve our understanding of the world and make our lives better in ways we can't yet predict. Despite the many challenges that remain in the search for axions, the excitement around their potential is undeniable. As researchers continue to refine their techniques and develop new methods of detection, the possibility of uncovering the true nature of dark matter seems more and more within reach. With the help of groundbreaking experiments, international collaborations, and the continued advancement of technology, we are moving closer to answering some of the most fundamental questions about the universe. If axions are indeed the key to unlocking the mystery of dark matter, the implications for physics and our understanding of the cosmos would be nothing short of revolutionary. The search for axions is also a reminder of the importance of scientific curiosity and persistence. The history of science is full of discoveries that seemed impossible at first, only to be proven true with time and effort. The existence of dark matter, the development of quantum mechanics, and the discovery of the Higgs boson were all once thought to be impossible. Yet through dedication and innovation, scientists have continued to make breakthroughs that reshape our understanding of the universe. The same spirit drives the search for axions, and it will continue to push the boundaries of human knowledge, regardless of the obstacles. Axions represent one of the most tantalizing and promising theories in the search for dark matter. If they exist, they could not only solve the mystery of dark matter but also revolutionize our understanding of the universe. Their discovery would open up entirely new realms of physics, from the nature of gravity to the connection between quantum mechanics and general relativity. The search for axions is a journey that could lead to answers to some of the deepest questions in science, and even if axions themselves are never detected, the technologies and ideas developed along the way will continue to shape the future of science and technology. In the quest to understand the universe, the search for axions is a critical piece of the puzzle, and one that will likely yield profound insights for years to come. As we continue to explore the nature of axions, we delve deeper into how they may fundamentally challenge and redefine our understanding of the universe. The implications for cosmology, particle physics, and the very structure of space-time are immense, making the search for these elusive particles not just a scientific endeavor but a philosophical one as well. The very act of searching for axions, and potentially finding them, could force us to reconsider what we know about reality itself. To truly grasp the significance of axions, we must first revisit one of the biggest unsolved mysteries of modern physics: dark matter. This invisible, mysterious substance makes up about 27% of the universe's mass-energy content, yet it cannot be seen directly. We know it exists because of its gravitational effects on visible matter, but it has eluded direct detection for decades. Current theories suggest that dark matter is composed of particles that interact weakly with ordinary matter, making them incredibly difficult to detect with traditional methods. Axions, as theorized particles, fit this description perfectly, adding a layer of intrigue to their potential discovery. Theoretical physicists have long wondered about what particles might comprise dark matter. One leading candidate is the WIMP, or weakly interacting massive particle, which is a type of particle predicted to interact through both gravity and the weak nuclear force. However, despite extensive searches using high-tech detectors, no definitive evidence for WIMPs has been found. In contrast, axions offer a very different potential solution, one that is still in the realm of the theoretical but has been gaining significant attention. Unlike WIMPs, axions would be incredibly light, so light, in fact, that they would have no measurable mass at all in the traditional sense. Instead, their properties arise from their interactions with electromagnetic fields, a characteristic that makes them quite different from anything else we have encountered in particle physics. This distinction is one of the reasons why axions are so compelling. Their theoretical behavior is predicted to be so unique that they could represent an entirely new class of fundamental particles, a discovery that would reshape our understanding of the universe at the most basic level. The search for axions is not just about confirming their existence as dark matter. Their discovery would have profound implications for other areas of physics as well. In particular, axions are thought to be tied to one of the most pressing challenges in modern physics: the unification of the fundamental forces. The four known fundamental forces, gravity, electromagnetism, the weak nuclear force, and the strong nuclear force, are currently described by separate theories. Axions could potentially play a role in unifying these forces into a single, cohesive theory that explains how they all interact at different scales. This could open the door to a theory of everything, something that physicists have been searching for more than a century. To put it simply, axions could be the missing piece in a puzzle that has eluded scientists for decades. If axions exist, they could explain the strange and unexplainable behavior of galaxies, clusters of galaxies, and other cosmic structures that seem to exhibit an unseen force at play. Dark matter's gravitational influence has been observed across the universe, from the way galaxies rotate to the way galaxy clusters behave. Without the presence of dark matter, these phenomena wouldn't make sense. Axions could be the particles that are responsible for these forces, providing the key to unlocking the mystery of the universe's dark side. So, how exactly do scientists plan to detect axions? Given their weak interaction with normal matter, detecting axions is no easy task. But researchers have come up with a variety of creative methods, each of which is designed to exploit the axions' unique properties. One of the most promising approaches involves using extremely sensitive detectors that can measure minute changes in electromagnetic fields. When an axion interacts with a magnetic field, it could convert into a photon, a particle of light. By setting up detectors in areas with strong magnetic fields, such as around superconducting magnets, scientists can look for these rare photon events as evidence of axions. In addition to direct detection methods, axions could also leave their mark on the cosmic microwave background (CMB), the faint afterglow of the Big Bang that permeates the entire universe. Axions could, in theory, influence the CMB in subtle ways, altering the patterns of radiation that we detect. By studying the CMB with greater precision, scientists may be able to detect the presence of axions indirectly. This would offer another path to confirming their existence and understanding their role in the cosmos. But these methods are not without their challenges. The sensitivity of the detectors must be extraordinary, and the signals they are searching for are incredibly faint. In fact, axions are predicted to interact so weakly with matter that their detection would require unprecedented levels of precision. This is why international collaborations, involving scientists from all over the world, are critical in this search. With access to advanced technologies and large-scale experiments, researchers are pushing the boundaries of what is possible, using everything from laser interferometry to superconducting sensors to look for axions. Another intriguing possibility is that axions could also help solve some of the greatest unsolved questions about the universe's early moments. For example, the origin of the matter-antimatter asymmetry is one of the greatest mysteries in cosmology. The universe is predominantly made of matter, with very little antimatter to be found. However, when the universe was created, it should have contained equal amounts of both. Something must have tipped the balance in favor of matter, but what that was remains unclear. Some theorists suggest that axions could play a role in this mystery, potentially providing a clue as to why matter is dominant in our universe. If axions can interact with other particles in such a way as to favor the production of matter over antimatter, they could be key to solving this puzzle. The implications of discovering axions extend beyond just particle physics and cosmology. Their discovery could also have technological consequences, potentially opening up new avenues for developing novel materials and devices. The techniques used to detect axions, such as superconducting sensors, advanced lasers, and ultra-sensitive photon detectors, could find applications in other fields, from medical imaging to quantum computing. As with many breakthroughs in fundamental physics, the ripple effects of axion research could extend far beyond the confines of particle accelerators and telescopes, influencing technology in ways that are difficult to predict. The quest to understand axions represents one of the most exciting frontiers in modern science. These ghostly particles could hold the key to some of the biggest mysteries in physics, from dark matter to the unification of forces to the origins of the universe itself. The search for axions is a testament to the power of human curiosity, and the willingness to push the boundaries of what we know. Whether or not axions are eventually detected, the process of searching for them will undoubtedly lead to profound discoveries, not just about axions themselves but about the nature of the universe and the forces that govern it. As we continue this search, one thing is certain: the mysteries of the cosmos are far from being solved, and the answers may be even stranger and more fascinating than we can imagine. The search for axions has far-reaching implications not only for our understanding of the universe but also for the future of physics as a whole. The possibility that these particles could explain dark matter has sparked a wave of new research, leading to new theoretical models and experimental techniques. Every breakthrough in this search brings us closer to solving one of the greatest mysteries in modern physics, and may even open the door to entirely new areas of science. As we've discussed, axions are highly elusive particles, and the reason they've remained undetected for so long is their incredibly weak interaction with normal matter. This weak interaction means that they are extremely difficult to observe directly, but it also means that they could be incredibly abundant throughout the universe without ever being noticed by conventional means. Unlike other particles, such as electrons or protons, axions wouldn't radiate energy or interact with electromagnetic fields in the same way, making them almost ghostly in nature. This ghostly quality is precisely why scientists think axions could be the dark matter that accounts for the unexplained gravitational effects observed in galaxies. Without dark matter, the motion of galaxies and galaxy clusters wouldn't make sense. Stars on the outer edges of galaxies would be flung into space due to insufficient gravitational pull from visible matter. However, the presence of unseen matter exerting additional gravitational pull holds everything together. If axions are indeed the culprit, they could make up the mysterious substance that keeps the universe in balance. But how can axions explain dark matter? It all comes down to their potential role in the mass-energy content of the universe. Axions are theorized to have a very small mass, which means they would be ideal candidates for forming the invisible matter that scientists have been searching for. As weakly interacting particles, they wouldn't give off light or heat, making them incredibly difficult to detect. But their gravitational effects, in turn, would have a profound impact on the structure of the universe, influencing the formation of galaxies and clusters. In essence, axions could be the very glue that holds the cosmos together, but their elusive nature means that we have to look deeper into the fabric of space to detect them. Understanding axions also requires understanding how they might behave in the context of the larger universe. One of the most exciting possibilities is that axions could also explain the phenomena of cosmic inflation, the rapid expansion of the universe that occurred in the first fractions of a second after the Big Bang. During this period, the universe expanded exponentially, and much of the energy from that time remains in the form of particles like axions. If axions exist, they could help explain how inflation occurred and what role they played in the formation of the universe we see today. In fact, some researchers believe that axions might have been produced during the early moments of the Big Bang, contributing to the structure of the universe even before galaxies formed. The theoretical framework that predicts the existence of axions draws from several areas of physics, including quantum mechanics, particle physics, and cosmology. The idea was first proposed in the 1970s as a solution to a problem in the theory of the strong nuclear force, one of the fundamental forces of nature that binds protons and neutrons together in the atomic nucleus. The strong force was known to violate a certain symmetry known as the CP symmetry, which governs the behavior of particles and their antiparticles. In 1977, two theoretical physicists, Roberto Pecchiai and Helen Quinn, proposed that axions could be the result of an interaction that restores this symmetry, and that these particles could be incredibly light and weakly interacting. Their theory was part of a broader effort to understand the properties of the strong force, but it also had the unintended consequence of predicting the existence of a new class of particles that might solve the mystery of dark matter. In the decades since the axion theory was first proposed, many other theoretical models have built on this idea, further refining the properties and behaviors of these hypothetical particles. Some of the most exciting developments have come from the realization that axions could be detected indirectly by their effects on magnetic fields and electromagnetic radiation. One of the key predictions of the axion theory is that axions should interact with electromagnetic fields in a way that could cause them to transform into photons, particles of light. By looking for these axion-photon conversions, researchers hope to detect the presence of axions, even if they are too faint to detect directly. One of the most promising methods for detecting axions is through the use of large-scale, sensitive detectors placed in strong magnetic fields. These detectors are designed to catch the rare axion-photon conversions that are predicted to occur when axions pass through a magnetic field. The conversion would produce a faint burst of light that could be detected by the sensors. In addition to these direct detection efforts, scientists are also looking for evidence of axions in the cosmic microwave background, CMB, the faint radiation left over from the Big Bang. As axions interact with the CMB, they could leave subtle imprints that could be detected by advanced telescopes and sensors. Another intriguing avenue of research is the study of axions in the context of astrophysical phenomena. For example, axions could be involved in the behavior of white dwarfs, neutron stars, and black holes, some of the most extreme environments in the universe. These objects emit intense radiation and can create strong magnetic fields, making them ideal candidates for axion research. If axions exist, they could play a role in the behavior of these exotic objects, potentially influencing the way they emit energy or interact with their surroundings. For example, axions could be responsible for the mysterious, fast radio bursts that have been observed in distant galaxies, or they could explain the way black holes emit energy as they evaporate. The discovery of axions could revolutionize our understanding of both the small-scale world of subatomic particles and the large-scale structure of the universe. They could provide the missing link between quantum mechanics and general relativity, two pillars of modern physics that have never been fully reconciled. Axions could also shed light on other fundamental mysteries, such as the nature of dark energy, the force that drives the accelerated expansion of the universe. If axions play a role in the dynamics of dark energy, their discovery could provide critical insights into the future of the cosmos. At the heart of the search for axions lies a deeper question about the nature of the universe itself. How did the universe come into being, and what is the fundamental structure of reality? Are there other dimensions beyond the ones we can perceive, and could axions be a clue to unlocking their secrets? The search for axions is not just a quest for a specific particle. It is a quest for understanding the very fabric of the universe. It is a search that could redefine everything we know about space, time, and matter. For now, scientists continue to refine their search techniques and develop new technologies to detect axions. While the challenge is immense, the potential rewards are even greater. If axions are discovered, they could provide the answer to some of the most profound questions in science. They could lead to a deeper understanding of dark matter, the fundamental forces of nature, and the origins of the universe itself. And they could open the door to new realms of physics that we can scarcely imagine. As we look to the future, the possibility of discovering axions serves as a reminder of the limitless potential of human curiosity, and the power of science to uncover the unknown. Whether or not axions are ultimately detected, the search for them is an essential part of our quest to understand the universe, and it will likely continue to inspire generations of physicists, astronomers, and curious minds around the world. The mysteries of dark matter, and the role axions may play in solving them, will keep us searching, questioning, and exploring the universe for years to come. As the search for axions progresses, the potential for a breakthrough remains tantalizingly close. However, discovering axions or even confirming their existence may take years, if not decades, of painstaking work. Yet, it's crucial to remember that the process of scientific discovery is rarely quick. It's a journey that often requires patience, innovation, and perseverance, with each small step revealing new clues about the nature of the universe. What may seem like a seemingly small finding in the grand scheme of things could, in fact, open up entirely new fields of research. In the grand narrative of cosmic mysteries, axions have earned a special place, not just because they might explain dark matter, but because they represent the frontier of human curiosity. For physicists, the pursuit of axions is not just a matter of detecting a new particle, it's about reshaping the very way we think about reality itself. The existence of axions could bridge gaps in our understanding of some of the most fundamental problems in physics. The implications of discovering axions would ripple across multiple domains. First, it would provide direct evidence for dark matter, a concept that has, until now, been inferred mainly through its gravitational effects. Currently, dark matter's existence is confirmed indirectly, by observing how galaxies move and how light bends around massive objects. However, without directly detecting dark matter particles, scientists are left with questions that remain unanswered. If axions do turn out to be the elusive dark matter candidates, it will solidify our understanding of the universe's missing mass. Secondly, the discovery of axions could have profound effects on our understanding of the early universe. If axions were indeed formed during the Big Bang, their properties could reveal information about the conditions that existed in those critical moments after the universe began. The role they played during cosmic inflation, as well as their interactions with other particles in the early universe, could provide vital clues to understanding the very origins of the cosmos. For cosmologists, this would be akin to finding a new piece of the puzzle in the quest to understand the formation and evolution of the universe. In a more practical sense, if axions exist and their interactions with electromagnetic fields can be harnessed, they might even have technological implications. For example, the ability to detect axions through their conversion to photons opens the door to more sensitive detection devices. These devices could be used not only to study axions but also to explore other phenomena in particle physics, such as the search for other exotic particles. The tools developed for axion research could be applied to a wide range of fields, from astrophysics to materials science, and potentially even in medical technology. One particularly exciting area of exploration involves the potential for axions to answer some of the biggest questions in quantum mechanics and general relativity. These two pillars of modern physics have yet to be unified into a single framework. Quantum mechanics, which governs the behavior of particles at the smallest scales, and general relativity, which explains the behavior of massive objects like stars and galaxies, are not fully compatible in their current form. Axions might serve as a key that unlocks the door to a unified theory, offering new insights into how the universe works at both the quantum and cosmic scales. Their discovery could be the missing piece in the puzzle that physicists have been trying to solve for over a century. The search for axions is also a testament to the power of collaboration across disciplines. Particle physicists, cosmologists, and astrophysicists from all over the world are working together, combining their expertise and resources in the hopes of solving one of the universe's greatest mysteries. This collaborative effort reflects the strength of the global scientific community, united by a common goal: to understand the fundamental nature of reality. In addition to the collaborative efforts on Earth, space-based experiments could also play a role in the search for axions. Observatories and space telescopes, such as the upcoming James Webb Space Telescope, could provide crucial data about cosmic phenomena that might help detect axions. For instance, axions could influence the properties of the cosmic microwave background (CMB), the afterglow of the Big Bang, or affect the way light travels through the universe. These subtle effects could be detected from space, allowing scientists to probe the farthest reaches of the cosmos while simultaneously searching for the elusive axion. Moreover, as the technology advances, so too does the sophistication of the experiments designed to detect axions. In addition to experiments on Earth, such as those using supercooled detectors and strong magnetic fields, there is growing interest in using superconducting cavities and even space-based interferometers. These methods are designed to detect the faintest traces of axions, capturing their interaction with light in a way that may lead to their discovery. The future of axion research lies in these innovative techniques, which combine cutting-edge technology with the mysteries of the cosmos. The pursuit of axions is also deeply connected to the philosophy of science. It's about asking big questions, questions that challenge the very nature of existence. In many ways, the search for axions represents the spirit of exploration and the human desire to understand the universe at its most fundamental level. Whether or not axions are ultimately discovered, the effort to understand them is a reflection of humanity's enduring curiosity and its drive to unlock the secrets of the universe. As we continue to probe the mysteries of dark matter and the behavior of axions, it's clear that we are entering a new era in scientific discovery. With the potential to revolutionize our understanding of the universe, axions stand at the intersection of theoretical physics, cosmology, and experimental science. The search for these ghostly particles is just one example of how far we have come in our quest to understand the cosmos, and how much further we still have to go. The discovery of axions may not only provide the key to understanding dark matter but also lead to a deeper understanding of the forces that govern the universe. It could be the beginning of a new chapter in the story of human knowledge, one that will ultimately change the way we see the universe and our place within it. For now, the hunt for axions continues. Scientists are pouring their efforts into a variety of approaches, each one promising to reveal new insights into the nature of dark matter and the fundamental workings of the universe. As more experiments are conducted, more data is collected, and new technologies are developed, the chances of discovering axions, those elusive ghostly particles, become greater. And with that discovery, the universe may reveal its deepest secrets, changing the course of science and human understanding forever. The journey of scientific discovery is never a straight line, but with each new piece of the puzzle, we get closer to the truth. In the case of axions, the search is more than just about finding a new particle. It's about finding a missing link that could change everything we know about the universe and our place in it. And as long as the search continues, so too will the excitement, the questions, and the potential for new, groundbreaking discoveries that may ultimately reveal the hidden fabric of the cosmos. As the search for axions intensifies, it's important to recognize the complexity and ambition behind this quest. The detection of axions, if it happens, will not only mark a major scientific breakthrough but could also reshape our understanding of the universe in ways we cannot fully predict. The particle, which could potentially solve the dark matter puzzle, is not just another hypothetical entity in the world of physics. It represents a key that could unlock a wealth of mysteries, from the makeup of the cosmos to the forces that govern reality. Dark matter is one of the greatest unknowns in modern physics. Scientists know it exists because of its gravitational effects on galaxies and clusters of galaxies, but they've never been able to directly observe it. Despite this, dark matter makes up about 27% of the universe's total mass energy content. If axions turn out to be the source of this elusive matter, it would not only confirm the existence of dark matter but would also provide the missing piece in the cosmic puzzle that has been unsolved for decades. Axions are theorized to be extremely light and weakly interacting particles, which is precisely why they have been so difficult to detect. Their faint interactions with other particles make them nearly invisible to conventional methods of detection. This is one of the reasons why axions have remained so elusive despite extensive efforts by the scientific community. But with advancements in experimental techniques and technology, there's hope that these ghostly particles will eventually be found. One of the major hurdles in axion detection is their weak interaction with ordinary matter. Because they interact so weakly, it's almost as if they pass right through matter, making them nearly impossible to observe directly. In essence, axions are like the universe's best-kept secret, slipping past every detector designed to find them. This is one reason why detecting axions requires such highly sensitive equipment and ingenious experimental setups. The theoretical framework behind axions stems from a broader theory known as the strong CP problem in particle physics. This is a problem in quantum chromodynamics (QCD), which describes the strong nuclear force, the force that binds quarks together inside protons and neutrons. The strong CP problem refers to a discrepancy between the predictions made by QCD and observations of particle behavior. The axion, as theorized by physicists, could be the solution to this problem, providing a mechanism that cancels out the asymmetry in the strong force. If axions exist, they could help explain why certain interactions in the universe seem to defy expectations. In 1977, physicists Roberto Pecchi and Helen Quinn proposed the existence of axions as a solution to the strong CP problem. Their theory suggested that a new type of particle, now known as the axion, could explain the lack of observed violations of CP symmetry, charge parity symmetry, in strong interactions. Axions, according to this theory, would interact with electromagnetic fields in a way that could have profound implications for our understanding of both particle physics and cosmology. Since then, many different experiments have been proposed and conducted in an effort to detect axions. These experiments typically look for the way axions might interact with light. One promising method involves using a strong magnetic field to convert axions into photons, particles of light. This process, called the axion-photon conversion, could allow scientists to detect axions by looking for faint bursts of light produced when axions interact with the magnetic field. These experiments, though incredibly challenging, could potentially lead to the first direct detection of axions. One of the most well-known experimental approaches to detecting axions is the axion dark matter experiment, ADMEX, which uses a large superconducting magnet to search for the conversion of axions into microwave photons. The experiment is designed to detect the faint signals that would be produced if axions exist and interact with the magnetic field. While the ADMEX has yet to conclusively detect axions, it continues to refine its techniques and improve its sensitivity, bringing us closer to what could be a monumental discovery in particle physics. Similarly, other experiments, such as the CASPER, Cosmic Axion Spin Precession Experiment, are investigating the possibility that axions could affect the spin of certain atomic nuclei. By measuring the tiny changes in the spin of particles, these experiments aim to detect the signature of axions and their interactions. The CASPER experiment, for example, is based on the idea that axions, if they exist, could cause a subtle shift in the alignment of nuclear spins. This shift could be measured with ultrasensitive equipment, potentially providing another avenue for axion detection. Space-based experiments are also exploring axions, as they may have detectable effects on cosmic phenomena. For example, axions could influence the cosmic microwave background, CMB, the afterglow of the Big Bang. The CMB provides a snapshot of the early universe, and any interaction with axions might leave an imprint on the data. Scientists are also investigating the possibility that axions could affect the way light travels through space, leading to observable effects in the light coming from distant stars or galaxies. Theoretical work on axions continues to evolve as well. Physicists are exploring a variety of possible properties for axions, such as their mass and how they might interact with other particles. These studies help inform experimental strategies and guide the design of future experiments. There's also growing interest in the role axions could play in the evolution of the early universe, particularly during the period of cosmic inflation, when the universe underwent rapid expansion. If axions are discovered, it would be a game-changer for our understanding of the universe. Not only would it confirm the existence of dark matter, but it would also offer new insights into some of the most profound questions in physics. For example, the discovery of axions could shed light on the behavior of the early universe, offering clues to the conditions that existed just moments after the Big Bang. Furthermore, understanding axions could help bridge the gap between quantum mechanics and general relativity, two of the most fundamental theories in physics that, as of now, remain incompatible. In addition to their potential to solve the mystery of dark matter, axions may have implications for other areas of science. For example, they could offer new insights into the nature of gravity, dark energy, and the fundamental forces that govern the universe. They could also inspire new technologies, particularly in the fields of quantum computing and particle detection, where advances in axion research could lead to breakthroughs in other areas of physics and engineering. Despite the many challenges involved in detecting axions, the search continues to captivate physicists and cosmologists around the world. The prospect of discovering a particle that could explain dark matter, unify fundamental forces, and provide new insights into the early universe is a powerful motivator for scientists working in the field. The journey of axion discovery, whether it results in a definitive finding or not, is shaping up to be one of the most exciting and important quests in modern science. With each passing year, new experiments are being designed, and new technologies are being developed to push the boundaries of our understanding. And although the detection of axions is still a distant goal, the very fact that we are getting closer to unlocking the mysteries of dark matter and the early universe is a testament to the power of human curiosity and innovation. The search for axions may ultimately reveal a universe far more complex and strange than we ever imagined. It could provide the key to understanding not just dark matter, but the very nature of the cosmos itself. And as scientists continue to probe deeper into the unknown, the discovery of axions, if it happens, will be one of the most profound breakthroughs in the history of science, an achievement that could change everything we know about the universe and our place within it. This video is for educational or entertainment purposes only, and information provided in the video may be incorrect. Like the video and subscribe to the channel for more such amazing videos.